Okay, back in year 10, or possibly year 9, you learned about electron configuration and how electrons filled orbitals 2, 8, 8. And they did that to gain better stability, and it was lower energy. So hydrogen would just have one electron and helium would have 2. And then we'd go up to another orbital and it'd be 2, 1 for lithium. And you kind of learnt that these numbers add up to the total number of electrons. Something like fluorine would be 2, 7. Neon would be 2, 8, and then sodium would be 2, 8, 1. And that model worked quite well. Now in year 13 you're going to be learning a different model which works better than this one. And that explains some properties and trends that you wouldn't be able to explain just with this model. So one way of helping to look at it is to see what some of these orbitals may look like. Now, just going to draw something out. Now, the orbitals start to have different names for a start. We call one an S, and it's a spherical shape. And these really aren't orbitals as you know them. The areas of probability where you're likely to find electrons. Electrons aren't quite as normal as we kind of had you believe, like planets orbiting a sun or something like that. It's completely different. And so they're just areas of probability. And it's not important to know too much about that. But when we start to fill orbitals, it is important to know how many electrons these hold. An s orbital only holds 2. P orbital will hold 6, but it'll be 2 times 3, so there'll be 3 orbitals, each of which hold 2 electrons, so that's a total of 6 electrons. A d orbital can hold 2 electrons, but there's 5 of them, so that can hold 10. Now, that may not make much sense at the moment, but don't worry about that too much. Now, these stair steps are going up in energy, so the higher in energy, the less stable something is. So if we have a look at S, it'll fill with 1 electron, and this funny little arrow I've just done here with the kind of little bit to the side is to show electron spin. Electrons have something we call spin. Now, again, it's not too important to know about this, but this would be the very first electron entering an orbital, and that would be the equivalent of hydrogen. And we would say it was a 1s1. Notice the little number here is the one that describes how many electrons there are. This first number 1, and the quantum number, is the energy level. S is the actual name of the orbital it's going in. It's kind of like an address. And we'll do another electron, so that pairs up, and that would be helium, and we'd say that's 1s2. And that's in the first energy level. And then we start going up. So this is the first one, and we go to the second one, and then each one of these are p orbitals. And then we go up again, and this carries on, and we'll eventually have to know how this works. And we go, the next one would be lithium, and that would be 1s2, 2s1, that would be lithium. Again, notice this 2 and this 1 adds up to 3. And then we'd go 4, and that would be beryllium, boron, and carbon, and nitrogen. And notice I'm putting these individual electrons here in their own p orbital, and that's because electrons repel each other with a negative charge. So it's lower in energy for them to occupy these orbitals by themselves. You don't have to explain that too much, but it's kind of helpful to know. So the way we'd write this one would be 1s2, 2s2, 2p3. And then we start filling up again. And this would now be the equivalent of 10 electrons. This would be 6, and this would be neon's electron configuration for the new way of writing it. And then we go to sodium, magnesium, and then again we'd start filling until we have these all full, and that would be argon. Okay? Now, you really just have to know this line here, except there is one unusual thing about it. Notice how for the first orbital there's just an S, second orbital there's an S and a P, so getting 2 types of orbitals for each number. 3 we get an S plus a P plus a D, and for 4 we would actually get 3 things, an S plus a P plus a D plus an E. But you don't have to know the 4f, and you also don't actually have to know the 4d orbitals either. So you only have to, in fact, know the first 36 elements. It makes things a bit easier. Now, the one thing that's kind of important as you fill them is you go from 3s to 3p. You'd think you'd go to 3d, but what we actually find out is as these energy levels go up, go from an S to a P to a D, is that this D energy level is actually higher in energy than the 4s, which would be down here somewhere. And that means instead of this happening, we in fact go to the 4s first and then to the 3d. So it's really this final one here that you have to know the order of. Then you just have to put the electrons in here accordingly to fill them to know the electron configuration. And that should be reasonably straightforward. So if you did cobalt, which has 27 electrons, you go 1s, 2s, 2p, you're putting the electrons in as you did this, so now 10 electrons, and then you go to 3s, 3p, and you don't go to 3s, you go to 4s, remember, and that gets filled, and you've now got 12, 18, 20 electrons, you've got 7 left, and that becomes 3d7. Okay? Now there is a shorthand way of doing this. So instead of doing it in such a long way, you can actually look at this, which has got 18 electrons, and they've got the same electron configuration of argon. So you could do it like this. You just have argon, and you go 4s2, 3d7. In fact, you can do this with neon. So anytime you have a noble gas which has a complete outer shell, you can use this to abbreviate some of the electron configurations. It just makes things a little simpler in some cases. So aluminium, which has got 13 electrons, you could go 1s2, 2s2, 2p6, 3s2, but 4, 10, 12, and 3p1, and that would be correct. But we could also now use the fact that neon has this electron configuration. You just go to the shorthand notation and would be finished here as well. Now, negative electrons are actually much harder. Sulfur's got 16 electrons, so if they're too negative, that means you're going to add 2 electrons to get 18. So that would be 1s2, 2s2, 2p6, 3s2, 3p6. Okay. Negative electrons are straightforward. Now with positive ions are not quite so straightforward. So if we were to look at iron, for instance, which has got 26 electrons, its electron configuration would be something like this. That. And that would now be 18, 20, 36. When you go to a Fe2+, you think you've removed the electrons from the orbital because you think, oh, that's what energy is conditions to remove. But what we actually find is removing from this is actually lower energy. So this would be 1s2, 2s2, 2p6, 3s2, 3p6, and the 3d6, because these 2 electrons are gone. That writing out the complete electron configuration up to bed here in this first one is a good idea before you do any further one. It's very easy to start making sense. Now for Fe3+, we just take away another electron from there and that would become 3d fine. Okay? So that would be Fe3+ now. Just to give you another example, nickel 2+, we need to write that up. Nickel's got 28 electrons. I'd be tempted to write them out like this. you've got 14, 12, 18 electrons, and that would be, that would be 28. Now to get rid of the 2 electrons to make it the nickel 2+, I'll just remove that, and that would now be the electron configuration of the 2+. It just kind of makes it more likely that you aren't going to make no mistakes. Now there's 2 other ones that you need to know. Chromium, copper. Now if you do chromium, you'd probably do it something like this. And you'd go through the process, and that would be 24 electrons. There's only one thing. What happens in reality, instead of being 4s2, 3d4, it goes to being 4s1, 3d5. What we find is that here, having a half full d orbital, gives it a special stability. It's kind of low in energy. And so it does this instead. Likewise, copper has a similar thing that it does. Instead of being 4s2, 3d9, which is what we'd expect, it actually goes 4s1, 3d10. Having a full outer shell actually does make it more stable. And so, those are the 2 exceptions. Okay, to sum up, you need to know this orbital series, and when you fill them up, the electrons go here as a superscript, and that should add up to the total number of electrons that you're filling with, so check that. Now, 4s and 3d, you have that unusual thing where actually the 4s fills first, and then in terms of positive ions, it's the 4s that empties first. You need to remember that. Negative ions are just normal, remember, they just have to take into account whatever negative charge it is, the extra electrons put in. And that copper and chromium are a little unusual. Chromium has that 4s1, 3d5, and that gives it a half shell, that gives it stability there. And copper has 4s1, 3d10. These are the only 2 that do this. So don't make any other atom do this unusual thing to try and get a full outer shell or a half shell. Copper and chromium are the only ones that do it. Okay? So if you remember the way these fall here, and especially positive ions, and the trick with those is to write them out as a normal atom first, and then remove the electrons. You're less likely to make mistakes, and you should be guaranteed to do a good job here.